All right, so this last part of 2.6, we're really looking at putting all this stuff together that we've learned thus far and figuring out how to plot a rational function basically by hand or just to give a sketch. So there's a list of rules here. Um, if you write the rational function as a p over q, where p and q are polynomial functions with no common factors, that's a key here. Determine whether the graph of f has symmetry is our first step. Remember symmetry, we have to plug in negative x and then see if that equals the original function. And then if it doesn't, then we would test to see if it equals negative f of x. You can find the y-intercepts by plugging in 0 in for x and solving the equation. You can find x-intercepts, if there are any, by solving the numerator p of x equals 0. Vertical asymptotes can be found by solving the equation that the denominator equals 0. Remember that horizontal asymptotes come from comparing the degree of the numerator and the degree of the denominator. Look for any holes, if there are any. Remember, that's when we have common factors between p of x and q of x. Plot at least one point between and beyond each x-intercept and vertical asymptote. That's really going to give you the shape of the graph. And then basically we're using all of that information to come up with a sketch of the graph. So for the following examples, we're going to do exactly that. So for this example, let's start with determining whether the graph exhibits symmetry. So again, it tells us to do that, right? We got to find f of negative x first. So plug in negative x, and what happens? Well, we get 3 minus 2 times negative x over 1 minus negative x. Minus 2 times negative x is plus 2x. So 3 plus 2x. And in the denominator, we get 1 plus x. This is not exactly the same as the original function, so this is not even. We then need to look at negative f of x. So what does that do? Well, that would give us, if we apply a negative, let's say, to the numerator, that would be this divided by 1 minus x. That gives us negative 3 minus 2x over 1 minus x. This is not equal to f of negative x, so this is not odd either. So it looks like it doesn't exhibit symmetry. All right. Next, we need to look for any y-intercepts. The y-intercepts are, as it says here, evaluating the function for x equals 0. So if we plug in and solve for f of 0, what do we get? Well, let's see. So 2 times 0 is 0. 3 minus 0 is 3. 1 minus 0 is 1. And we get 3 out of that. So it looks like an intercept, and particularly the y-intercept, is x equals 0, y equals 3. Okay, so far we've got symmetry. We've got the y-intercept. We find the x-intercepts by setting the numerator equal to 0 and solving. Well, this isn't too much of a challenge, right? We move the 2x to the other side by adding, and then divide by 2. So we get x is 3 halves. Or if you'd rather, the point is 3 halves 0. Okay? That's our x-intercept. Find any vertical asymptotes. So how did we go about doing that? Well, let's double check, right? Vertical asymptotes by solving the denominator equals 0. Okay, so 1 minus x is equivalent to 0. Move the x to the other side by adding. That makes this x equals 1. So this is a potential vertical asymptote. I say potential because we could have a hole, right? But we'd have to have the same factor in the numerator and the denominator. All right, find any horizontal asymptotes. So again, to do that, we're comparing the degree of the numerator and the degree of the denominator. So let's see, right? Both cases we had negative 2x and we had x in the denominator, or negative x. So the degrees are degree 1 for both numerator and denominator. If the degree of the numerator is equivalent to the degree of the denominator, so if the degrees are equal, then the leading coefficients tell us the equation. So it'd be y equals negative 2 over negative 1, right? If we scroll back up here, the leading coefficient here is negative 2, here it is negative 1. So that gives us the equation y equals 2 for our horizontal asymptote. Okay. Last thing they asked us to do, or sorry, second to last, says find any holes. That would require for the numerator and denominator to have the same factor. But the numerator can't be factored, right? 3 and 2 don't have a common factor. There's no common factor of an x in there. So we can't do anything with that numerator. So we're going to say that there's no holes. And the last part says graph some other points. So actually, I'm going to go into the next page here, and we need to keep track of everything we have. So no symmetry. Y-intercept is 0, 3. Okay. For this last part, right, we need to keep track of everything we had. So I'm going to start my sketch here. So y-intercept at 0, 3. So I go up 3, I have an intercept there. I touch the graph. Then I also intercept at 3/2, 0. So 3/2, that's 1.5. So I touch right here. Then I have a vertical asymptote at x equals 1. So that's here. Then I have horizontal asymptote at y equals 2. So that's here. Okay. Now we can see why we don't have symmetry. Then there's no holes, and we just need to plot a few more points. So let's let x equal 3 would be a good one. So we need the function evaluated at 3, right? So we can get a point over here. Let's let, let's see, x equal maybe -1. And let's go from there. So the original function, let's just go back up. I believe it was 3 minus 2x over 1 minus x. So f of x is 3 minus 2x over 1 minus x. Plug 3 in. 3 minus 2 times 3 over 1 minus 3. So that's going to be 3 minus 6, or -3. Then divided by 1 minus 3, which is -2. So we get 3/2 again. So when x is equal to 3, y is equal to 3/2. So it looks like we're up here. And then when f is -1, what do we get? So we have 3 minus 2 times -1 over 1 minus a -1. -2 times -1 is 2. So we have 3 plus 2, which is 5. 1 minus a -1 is plus, so that's 2. So when x is -1, then we have 5/2. That's 2.5. So we're up here. So I believe that this is going to look something like this. from the points that we plotted in the asymptotes. Of course, I'm going to go to Desmos and get a nice picture because mine's not the greatest. So let's go do that. All right, so I went ahead and plotted the function 3 minus 2x over 1 minus x. I've also went ahead and put in the asymptotes x equal 1 and y equal 2. And you can see that we have a pretty good idea of what this thing would look like. So my sketch wasn't the greatest, but it was, in fact, a decent representation of what the function looks like. Okay, so let's look at example 2. Again, we want to determine whether the graph exhibits symmetry. So to do that, we need to go ahead and plug in negative x and see if we get back the same thing. So doing that, I get negative x squared is positive x, quantity squared. And so I get x squared minus 4 in the denominator as well. That is, in fact, exactly the same as the original function. So this has symmetry about the y-axis. Okay, that's nice. What's next? Find the y-intercepts. Remember, to find the y-intercepts, we are looking for when this thing is, or when x is 0. So we're looking for g of 0, which really just means plug in 0 everywhere. Right? So 2 times 0 becomes 0. Then we have negative 4, but it doesn't matter because it's divided by 0. So it looks like we go through the origin, 0, 0. So to find the x-intercepts, we need to figure out where is the numerator equal to 0. So we need to set 2x squared equal to 0. We would divide by 2, which would be x squared equals 0. Take the square root, and we get x equals 0. All right, so that is our x-intercept, which just so happens to be the exact same thing as the y-intercept. So there's only one intercept for both, and it's the origin. What about vertical asymptotes? So to find vertical asymptotes, then we need the denominator to equal 0. So now we're looking at where does x squared minus 4 equal 0. All right, so move the 4 to the other side by adding 4. Then take the square root. Remember, we get plus and minus. So this is x equals plus and minus 2. So we have 2 of them, right? It's negative 2 and x equals 2. And these are our vertical asymptotes. All right. We would like to find the horizontal asymptotes. So to do that, we need to compare the degrees. So remember, right, for the original function, we have 2x squared over x squared minus 4. So the degree of the numerator is 2. The degree of the denominator is 2. So if the degree of n is equal to degree of d, then remember the line y equals the division of the leading coefficients, right? There'd be a 1 down here, gives us the horizontal asymptote. So it looks like y equals 2 is our horizontal asymptote. Okay. What else do we need? Are there any holes in the graph? The holes would occur if we had the same factor in the numerator and denominator. We can go ahead and factor this, but it's not going to really help us much because we're going to see that there aren't any holes, right? It's 2x times x if you want to factor that. X squared minus 4 becomes x minus 2, x plus 2. And by the way, that's how we can very easily get our vertical asymptotes there. So none of these factors in the denominator happen in the numerator. So there are no holes. And now we just need to plot. So we need to take all the information that we have. We know that we're symmetric about the y-axis. We go through the origin. We have vertical asymptotes at -2 and 2, and we have a horizontal asymptote at 2. So let's see if we can't put all of that together and create a sketch. All right, so let's maybe do 5 tick marks on each side or so. And again, this is not the greatest plot in the world. Right, it's just a sketch. So I know I go through the origin. I know that y equals 2 was an asymptote. I know that x equals 2 is an asymptote. And I know x equal -2 is an asymptote. All right. Well, right now I don't know anything about what's going on in any of these other regions, right? I just know that I go through 0. Were there anything else that we found? I think that was it. So now we need to plug in some points to see what this thing is doing. So let's plug in -1 and +1 into the original function. Right, so I think it was g of x, and that was 2x squared over x squared minus 4. So what is g of -1? Okay, so let's plug that in. So -1 squared is +1, times 2 is 2, -1 squared is 1, minus 4 is -3. So it's at -1, -2/3. So somewhere down here. Well, let me use the right color. So somewhere down there. If I plug in 1, right, we said that this thing was symmetric, so it better have a point on this side that looks very similar. Okay. So it looks to me like I think it's going to do this in between, right? And it's going to get a little closer to the asymptote. Just it needs to do it a little further away. And then I think what's going to happen, I think we're going to get one up here. And I think we're going to get one up here. So let's just plot a point. Let's see, when x is 3. So g of 3. So plug that in. So we have 9 times 2 is 18. 9 minus 4 is 5. That's not very nice, but we at least know it's a number that's bigger than 2, right? So when x is 3, we know we're up here somewhere. And let's do, again, well, again, we don't have to do -3, right? We know that it has to have symmetry, so it should also be at the same point. So another point up here. And you'd want to plot a few more points, but you know, I have a little bit of prior knowledge of what these type of things look like. So let's go ahead and jump on over to Desmos and take a look at the actual plot so that it's a little bit clearer for us. Here you can see the equation plotted in red, and you can see the asymptotes already on the curves or on the Cartesian plane. And you see that the shape follows exactly what we had thought from our sketch. And again, there's symmetry and all of the correct asymptotes are shown. So this is great. We've starting to learn how to correctly come up with a sketch of one of these functions. So here we have the final example for 2,6 rational functions. Again, the first thing we want to do is look for symmetry. So we need to plug in f of -x. So we have -x plus 2, and then we're going to get x squared plus, or sorry, minus x minus 6. This is clearly not the same as the original, but it could be -f of x. So we need to find out what that looks like. We would apply a negative, let's say, to just the numerator, which I'm writing incorrectly here. Here we go. X plus 2, x squared plus x minus 6. Now that's going to make everything negative up here. So this is also not equivalent to the f of negative x. So it appears there is no symmetry. All right. Find any y-intercepts. So remember, to find the y-intercepts, we need to figure out where is x equal to 0. So we plug in 0 to the entire function. And what do we have? Looks like 2 over negative 6 or negative 1/3. So we have for the y-intercept the point 0, negative 1/3. All right. What about the x-intercepts? So to find those, we need to find where y is 0. And that means we need to set the numerator equal to 0. So x plus 2 equals 0. Move the 2 to the other side, and we get x equals negative 2. So this is going to give us our x-intercept, and that's going to be the point negative 2, 0. All right, we've got a decent amount of information so far. What about vertical asymptotes? This is where the denominator is equal to 0. To solve this, we need to factor. So we're looking for two numbers that multiply to negative 6 and add to 1. Those two numbers are plus 3 and minus 2. Then if we set each one of these equal to 0 separately and solve, we get x equals negative 3 and x equals 2. So we have potential vertical asymptotes at these two values. I say potential because one of them could potentially be a hole. All right, horizontal asymptotes. We have to look at the order or the degree, right? The numerator is degree 1. So we have degree of the numerator is degree 1. It is less than the degree of the denominator. Let's just jump back up really quick. So we said that degree of the numerator is less than degree of denominator. Y equals 0 is our horizontal asymptote. So for the example we're doing, right, that is the case. So y equals 0 is the horizontal asymptote. All right. Potential holes, we'd have to factor the entire function. It's already x plus 2 on top, so that's not too bad. Then we have x plus 3 and x minus 2. So these are not quite the same, so no holes. And therefore, both of these are, in fact, vertical asymptotes. Now, if this was plus 2 down here, right, that would be a hole, and the only vertical asymptote would be x plus 3. So keep that in mind. Last thing is to plot these on our sketch and then determine if we need any other points. All right, so we go through the point 0, negative 1/3, negative 2, 0. So let's plot those first. So it was 0, negative 1/3, so that'd be down here somewhere. And then the other was what, 2, 0, I believe. Sorry, negative 2, 0. So negative 2, 0. So we go through this point and we go through that point. All right, asymptotes were x equal negative 3 and x equal 2. So x equal negative 3 would be there, and I missed my point. And x equals 2. Okay. Then we had a horizontal asymptote at y equals 0, so just the x-axis. Again, remember, it's okay if we cross as long as that the behavior at infinities, negative and positive infinity, never touches that asymptote. All right, so we need a little bit more here to go by to figure out what this guy's going to do. So let's plug in, let's see, maybe -1 into the function. So the function was x plus 2 over x plus 3 and x minus 2. We said we're going to plug in -1. So -1 plus 2 over -1 plus 3, -1 minus 2. Okay. So it looks like we get 1 over 2 times -3, or -1/6. So when x is -1, we're at -1/6. So it's getting even closer to that point. Okay, let's do 1. So if we plug 1 in, I don't remember, I think it was h of x, but just bear with me if I called it g. So g of x, or g of 1, that'd be 1 plus 2 over 1 plus 3 and 1 minus 2. So that's 3 over 4 times -1, or -3/4. So when x is 1, we're at -3/4. So that's down here. Okay, so it looks like it's kind of curving downward here. I missed my point there. All right, let's continue to plug values in and see what's going on. So let's plug all right, so we would need to continue to plot points getting close to -3 and close to 2. What we'll see is that it's going to continue to fall on this end, and it's going to increase on this end. And then we're going to get a piece down here. So if we plotted some points over here, we'd get this shape. And then same thing over here, we'd get this shape. I just don't want to bore you with plugging in a bunch of points. You could literally just choose a few of them, or maybe even just maybe make a table in your calculator without going right to the image. And lastly, let's just jump over to Desmos as always. Functions plugged in there. This is the equation. I didn't plot the asymptotes, but you can see them pretty clearly there, right? We wouldn't touch -3, we wouldn't touch 2, and then you'll see that even though this part passes through the axis, as we go to -infinity and positive infinity, we never touch the x-axis. So that'll conclude 2.6, and I'll see you for the next set of videos.